The model airfoil is placed in the test section of the wind tunnel. It is supported by wires which will transmit its lift and drag forces to the scales. Tubes which connect to the test points are passed through an opening in the tunnel wall and connected to the manometer bank. The manometers, being at equal pressures, are at the same level and are connected to the airfoil. Thus, from each manometer tube, there is a direct connection to a definite point on the surface of the model airfoil. All is now ready for the test, and the engineers leave the tunnel to take up positions where they can observe and measure reactions upon the airfoil. The motors which drive the fans are started. In the tunnel, the model airfoil is subjected to the same conditions which it would encounter in actual flight through a medium of the same density, and pressures along the surfaces are at such values as would be met under flying conditions. The manometer tubes tell the story. Levels fluctuate slightly as minute variations in airspeed or density occur, but the ratios are constant, and the position of the liquid in the tube shows both positive and negative values for the airfoil. The tubes are photographed to assure simultaneous readings of all tubes, and the photograph is used by engineers to plot the pressure curve. In this manner, a diagram is constructed showing the nature and distribution of pressures over both surfaces of the wing section at varying angles of attack. Positive pressures are shown in black, negative in gray. At 0 degrees, there is a small bulb of positive pressure directly upon the leading edge of the wing. Another area of positive pressure encloses the trailing edge and extends forward about 1/4 chord length along the lower surface. Elsewhere, the pressures are negative. As the angle of attack is increased, the positive pressure bulb moves lower down on the leading edge and back along the lower surface of the wing, enclosing the trailing edge. The negative pressure distribution remains fundamentally unchanged, although its values are greatly increased. This diagram indicates that the wing has begun to exert a considerable lift. Increasing the angle of attack still further alters pressure distribution very little, although there is a marked change in values, particularly along the upper surface, where negative pressures are now exerting a powerful lift force. The wing is now approaching its stalling angle, positive pressures have changed very little in either distribution or value. The negative values, however, have increased somewhat, especially at the leading edge. By further increasing the angle of attack, positive pressures remain practically unchanged in both value and distribution, but the value of negative pressure continues to increase. At this angle of attack, the wing is well past its stalling angle, yet the positive pressures show little indication of change. With the negative pressures, the greatest change is noticed at the leading edge of the wing, where the area continues to expand, and the outline of the pressure area is extremely irregular. Increased angle of attack brings no important change in positive pressure value or distribution, but the negative pressure area is tending to equalize in value over the entire upper surface of the wing. At this angle of attack, the forward protuberance disappears completely, and an area of nearly equal negative pressure blankets the entire upper surface of the wing. Positive pressure areas still show no important change. Another increase in the angle of attack merely results in increased values, distribution remaining almost the same as before. At this final angle, pressures have reached still greater values without any appreciable change in distribution. It might appear from this diagram that at this angle of attack, the uniform pressure distribution over the upper wing surface would be desirable. However, above the stalling angle, the resultant air force acts in such a direction that the drag is its large component. An airfoil at rest in still air is at atmospheric pressure over its entire surface. It has been shown that airfoils derive their lift from the pressure differences acting upon their surfaces, the negative pressure difference upon the upper surface at normal angles of attack being the major component of the lift force. Now let us see what happens to pressure values and distribution at negative angles of attack. From 0 degrees, the angle is decreased to a slight negative value. The positive pressure bulb on the leading edge is practically unchanged. The negative pressure on the upper surface of the wing shows little change. However, the negative pressures along the lower surface begin to increase at the leading edge. Further increases in this area, accompanied by very slight changes in the positive pressure bulbs, are the only differences which are readily observable as the angle of attack is further decreased. The angle of attack of an airfoil was shown to be the acute angle between the chord of the airfoil and the relative wind. The angle of attack of the airplane as a whole is the acute angle between the longitudinal axis of the airplane and the relative wind. The difference between these two angles is constant for any given airplane and is called the angle of incidence. Although the angle of attack is constant for any given wind tunnel test, in actual flight the angle of attack of the airfoil varies with changing attitude and speed of the airplane. Consider the case of an airplane flying horizontally at a small positive angle of attack. As the controls are set to put the airplane into a dive, the angle of attack decreases and the speed increases. Lift decreases, since in this attitude the weight of the airplane is opposed by the resultant of lift and drag. As the flight approaches the vertical, speed increases until the terminal velocity is reached in the so-called vertical dive. In this condition, lift is zero, and the weight of the airplane plus its thrusts are opposed by drag alone. In pulling out of the dive, the angle of attack must be increased slowly. During this maneuver, the lift may attain several times the value of the weight. This increase in lift produces acceleration, which in turn produces a curved flight path.